Today, our first speaker is Matthias Flack. He will continue on special values of motivic L function. Yeah, over to you, Matthias.
All right, thank you. Good morning, everyone. So as I was outlining yesterday, I'm continuing on motivic L functions, and the nature of my talk is mainly instructional. So I will talk about work of many other people, some of which are listed here, and which has converged to a conjectural picture on motivic L function special values, which by now is fairly classical. It's maybe 30 years old. Okay, so I want to start with a general formulation. And so I have to say something about motives and motivic L functions. So the basic input is geometric. One starts with a smooth projective variety over Q. And then an L function is attached to a direct summand of the cohomology or the motive of such a variety. And a category of motives has been made precise, for example, in the work of Voevodsky or Levine or others. But that's a triangulated category called DM GMQ with Q coefficients. Whereas we would be interested in an abelian category of motives, which would be the heart of a T structure on this DM. And this hasn't been constructed yet. So there is no rigorous theory of motives. There's only expectations, for example, that the total motive of X splits in this category into a direct sum of its HIs in each degree, that the HIs are cut out by correspondences, but that's not known. So we switch to the traditional point of view of a motivic structure, which is just a linear algebra construct reflecting the structure you should get from a motive. So we don't know what a motive is, but we know what a motivic structure is. It's unfortunately quite complicated. But roughly you could think of it as a ith degree cohomology of X with a J twist for I and J integers. And then you have realizations, which means these are concrete cohomology theories which can be actually rigorously constructed and which should be reflecting this properties of this motive HI. So the L-adic realization would be a continuous Galois representation gotten by scalar extension to Q bar and taking usual étale L-adic cohomology. The Betti realization M Betti is what's called a Q-hot structure over R, gotten from the complex manifold of complex points X of C. And then one has the de Rham realization, which is a filtered Q vector space. And so these are theories that can be rigorously constructed, and they have parallel properties. They reflect common properties of this HI. For example, they all have the same rank over the corresponding coefficients, like ML is of the same dimension over QL as M Betti is the dimension over Q, and so on. And these are QL vector spaces or Q vector spaces. And then when you tensor, for example, M Betti with QL, there's a comparison isomorphism. So that implies that the group spaces have the same rank with the L-adic realization. And you have a Betti-de Rham comparison isomorphism. And you also have an L-adic de Rham comparison isomorphism over some slightly more mysterious field B de Rham. So that's not the p-adic completion of QP bar. So that leads into p-adic Hodge theory, which was the main technical input that enabled Bloch-Kato to formulate the conjectures to begin with in the late 80s, after p-adic Hodge theory had been invented by Fontaine. Okay, so this motivic structure is some linear algebra structure consisting of all this ML, M Betti, M de Rham with the comparison isomorphisms. And once you have this structure, you can associate an L function. So you form the characteristic polynomial of Frobenius acting on the L-adic cohomology, but to have a well-defined action, you take invariance under inertia. If P is a prime of good reduction, then inertia already acts trivially, and you already have a Frobenius action on the L-adic realization. And this is where the first conjecture comes in. One is expecting this polynomial, even though a priori it has coefficients in QL, to actually have coefficients in Q and be independent of L. But at the bad places where inertia acts non-trivially, this is not known in general. It's known for the good places. So for each prime, you get an Euler factor, and then you form the Euler product by plugging in p to the minus s for the variable t. And this will converge for weight reasons if the real part of s is bigger than 0. So that's the motivic L function. And here's a list of some examples. As we saw in the first talk, the Dedekind zeta function is an example. If you plug in Qj, you get a shifted Dedekind zeta function. So by this shift, we can always reduce special value conjectures to s equals 0. And if you take, for example, a number field like Q adjoint square root of -1, then it has a Galois action by the cyclic group of order 2, and it splits into the plus and minus eigenspace of this Galois action. So that's a sum in the category of motives. M splits into Q0 plus Q epsilon, which is associated to the non-trivial quadratic character of this Galois group. And its associated L function is a quadratic Dirichlet L function. So these were 0-dimensional examples. If you take a 1-dimensional example, take an elliptic curve like the Gauss curve, y squared is x cubed minus x, then because the curve has complex multiplication, one can identify the L function of the h1 of E over Q with a Hecke L function. And this was a class of L function for which the good analytic properties that one in general expects were known at the earliest. Already Hecke in around 1920 proved the analytic continuation of these Hecke L functions. But they weren't viewed as being attached to this elliptic curve. I think that came with Hasse and Deuring and Wey. And then you have non-CM elliptic curves like this one of conductor 37, and by well-known work of Wiles and others, it's in fact also an automorphic L function attached to a weight 2 U form. So as I was saying at the beginning yesterday, the only way to prove something about these motivic L functions is to identify them with automorphic L functions. And this is what this list shows actually. Okay, so the general expectation is that you can meromorphically continue such a motivic L function to the whole complex plane. And then you have a functional equation once you also add infinite Euler factors. So this L infinity MS is basically the Euler factor coming from the real place. So it's before it was an Euler product over all primes. Now we throw in the one infinite place of Q. So our base is always Q, even though one could make this whole story over any number field. But it's easy to reduce to the base field Q. And this infinite Euler factor is determined by the Hodge structure on the Betti cohomology. So I don't want to say more about this. Hodge structure means if you tensor the Betti realization with the complex numbers, you get a bigrading on it, and the dimensions of these graded objects are HPQ. And you throw in these gamma factors involving the gamma function. So this was first defined by Serre, and it's a recipe that works. It's not actually clear from an arithmetic geometry point of view where these gamma factors should come from. From an automorphic point of view, it's a bit more understood perhaps, but not at all from arithmetic. Okay, and when is this known? Again, in the 0-dimensional case, so for any x, the h0 of x would be the same as the h0 of the constant field of your variety x. Then again, you reduce to Dedekind zeta functions. And the functional equation is known. And whenever you have an identification with an automorphic L function, it's also known by automorphic theory. Like for an elliptic curve over a number field, again, over Q, modularity is known. And I think so this is probably not an up-to-date list. Over real quadratic or cubic fields, one knows the holomorphic continuation. because one identifies the L function of the H1 with an automorphic L function. And over generally totally real OCM field, I think one knows potential automorphy. So after some finite base extension, one has meromorphic or holomorphic continuation, and that can be massaged into proving meromorphic continuation over a given totally real OCM field. So a lot of this is known by work of Taylor and many others, Clauzel, and building on the Taylor-Wiles method, basically. And then if you have a curve like the Fermat curve that I was writing out here of exponent n, it's again the case because this curve has so many symmetries that you can identify its L function with the Hecke L function like in the previous example. So for the H1 of that Fermat curve, continuation is also known. For symmetric powers, it's known first meromorphically by, again, Taylor and Clauzel and others and Harris, and then also by recent work of Newton and Thorne. It's actually, you actually have holomorphic continuation. And probably for many Shimura varieties, you know the L function of the HD has the expected properties. So for special value conjectures, we only need meromorphic continuation. That's good enough because we want to describe the leading Taylor coefficient. Okay, now for something a bit more complicated and unintuitive. So this M not only has its realizations, which was these Q vector spaces M Betty, M de Rham, and the QL vector space ML. It also has motivic cohomology associated to it. So this is not a realization, it's like an X group in the category of motifs in which this M lives. So one has only two X, H0 and H1 in this category DM conjecturally. And concretely, they can be expressed in terms of K groups and Chow groups by the recipe I was writing down here. And everything is tensored with Q. So these are, again, Q vector spaces that one can attach to this motif. And yeah, so, okay, everybody can read it. I'm not going to read it out. So the K some index is an algebraic K group, as briefly mentioned yesterday, tensored with Q. And the upper J refers to an eigenspace for the Adams operators acting on this K group. So this didn't play a role for the Dedekind zeta function yesterday because the eigenspaces are neatly separated. They only occur in 2 consecutive degrees. But in general, this will split into different eigenspaces. A given K group will split into different eigenspaces for the Adams operators. Okay, and one thing I haven't written down, but I should, so let me write it down with my pencil here. Throughout, we have to assume that these groups are actually finitely generated. So these are, I mean, this is the deepest conjecture of all of them, I believe. And you can circumvent that by just writing down a subspace and replace the whole motivic cohomology by a subspace. But this is really cheating. I mean, so the big input here that you should assume throughout, even though I haven't written it down, is that these are actually finite dimensional Q vector spaces. So let me assume that throughout without saying anything more about this. And then we're not quite yet there. There are these F modifications of H0 and H1, so H0F and H1F, which basically means we're not interested in the generic fiber, but we're interested in an integral model, or rather what's left from the integral model in the generic fiber. So this, we take an image of an algebraic K group of a regular proper model, and one can show that this image is actually independent of the model. Yeah, so that's already indicating that you cannot avoid the arithmetic scheme actually in these conjectures. And in my last two talks, I will say much more about that point of view. But that's how it's traditionally done, going back to Beilinson. And so one has a slightly smaller K group H1F, which comes from an integral model. So the index sub F should mean coming from some integral model. Okay, so now the point is we have all these Q vector spaces, but once you tensor them with R, they're related by various maps. So this is this conjecture mod infinity. So first of all, we have the comparison isomorphism Bethe de Rham over C, and complex conjugation acts on both sides. If you take the invariants, then the M de Rham tensor C becomes the M de Rham tensor R. And so you get a map alpha M from the Bethe plus space tensored with R to M de Rham, and we divide out M0 de Rham tensored with R. So this was what Fontaine calls the tangent space of the motive. So this thing here is the tangent space of the motive. Yeah. So this is a modified period map alpha M, and the co-kernel of alpha M, and sometimes it also has a kernel, is kind of a variant of Deligne cohomology, or it's a part of Deligne cohomology that's cut out by the correspondences giving you this motive. But one can view it as a pure linear algebra construct. And then this conjecture mod infinity means that we also have a relation to the motivic cohomology groups tensored with R. So after we tensor these Q vector spaces with R, there are maps relating them. And the first map is a cycle class map. So remember, the H0 is basically a Chow group modular homological equivalent. So it's the part of cycles that survive in the Bethe cohomology. And the exactness of that sequence is basically a variant of the Hodge conjecture, that the algebraic cycles, the images of algebraic cycles, are just the F0 part of the rational. Or in this case, the real Hodge conjecture, because I tensor with R. And then I also have a height pairing implicit in this sequence, which basically only happens if M and M star 1 are both non-zero. That only happens at the central point, where M is basically isomorphic to M star 1, like in yesterday's talk of Yifeng, when you have a central point. And you have a height pairing H, otherwise these spaces are, one of them is 0. And then you have a regulator from the motivic cohomology H1F M tensored with R into the co-kernel of this alpha M. Again, this is some Deligne cohomology group. So this exact sequence is what relates all these spaces after tensoring with R. And again, it's known only in a few cases. So I mean, we have this dual motive occurring. So this is actually a little bit out of the blue. What's really happening, or how one should view this exact sequence, maybe I should, maybe I'll write it on the next slide. So there's actually some long exact sequence involved that sort of defines a compact support motivic cohomology. Then there's a duality involved, identifying compact support with a dual of usual motivic cohomology of the dual motive. So one should really understand this exact sequence in 2 steps. Okay, so now what we want to do is we want to look at the Taylor expansion of this motivic L function. And again, we can renormalize to S equals 0. Then it has a leading coefficient L star of M, which is just a non-zero real number. And it has a vanishing order R of M, which is some integer C. And we want to describe these 2 quantities in terms of the data that I've introduced so far. And for the vanishing order, it's just this expectation here. So the vanishing order R of M is the dimension of H1F minus the dimension of H0F of the dual. Actually, exactly as in the talk yesterday, where M was isomorphic to M star 1. So one can replace it with M. I mean, Yifeng Liu's talk, the central point. But this should be the formula for all points. The vanishing order is given by this. And again, if you don't like the appearance of the dual, you can think of this as some kind of compact support motivic homology. So this would be some H1C of M, but yeah, so now the compact support only exists with R coefficients. Well, yeah. Okay, that's not the right point to introduce this. Okay. So when is such a formula known? Again, the basic case of a number field, we have the Dedekind zeta function being the motivic L function of H0 spec F. And it is known that these groups are finitely generated, namely they just coincide with the K groups of the ring of integers in that case. And so by Borel's computation that I mentioned yesterday, and the known properties of the gamma factors, they exactly have the right vanishing order given by the rank of this K group. If J is less than or equal to 0. If J is -1, of course, we have a pole of the zeta function that's well known at S equal 1. If J is 1, S equal 1. And then the vanishing order is -1. So that's the only situation where this H0 of M star 1 is non-trivial. And then if J is greater or equal to 2, the Euler product converges and the function has a non-zero value, so the vanishing order is 0. So everything's known in this case. And some other cases where the vanishing is known is for an elliptic curve, so that would be the motive H1 twisted 1, where the vanishing order is less than or equal to 1. So by work of Gross-Zaghi and Kolyvagin, the vanishing order coincides with the rank of the group of points in that case. And for individual examples, one can also show that the rank agrees with the vanishing order if the vanishing order is 2 or 3 in some cases. Maybe I shouldn't spend too much time on this, but let me correct this. So there shouldn't be a cross here. And here I want to write dimension over Q. Okay. So that's the vanishing order. The next step, we want to describe the leading coefficient L star of M. And that's where the fundamental line comes in again. So there's a general recipe that produces this psi of M, which it's just a one-dimensional Q vector space, an invertible Q module made out of determinants of all these rational spaces that I remind you should be finite dimensional in general, and the rational space is coming from the Betti and the Ram realization of the tangent space. So there's some recipe. And if you look at this conjecture mod infinity, this long exact sequence that we had here, once you tensor all these spaces with R, all the spaces in the fundamental line will occur. So we have motivic homology of both M, H0FM, and H1FM in this sequence. We have the motivic homology H1F and H0F of the dual. And then we have the kernel and co-kernel of alpha M, but this involves, alpha M involves M Betti plus and M0 in the tangent space. So these are exactly the 6 Q vector spaces that occur in the fundamental line. And the fact that there are maps between them after tensoring with R means the fundamental line is trivialized by this isomorphism of theta infinity. After you take determinants on this long exact sequence mod infinity. And so the L value being a real number lives in the left-hand side of theta infinity in R. And the conjecture says that if you map it into the right-hand side by all these regulator and height pairing and period maps, it actually lies in this rational structure psi of M, this rational subspace of this real subspace. So that amounts to a rationality conjecture. It pins down the L value up to an unknown rational factor. But inside the real numbers, that's already a big step of describing it completely.
Related to Deligne's rationality conjecture?
Yeah. So Deligne concerned the critical case where alpha M is an isomorphism. So that means, let me write it out here. So M critical means that alpha M is an isomorphism. So that means the kernel and the co-kernel are trivial. And if you look at this exact sequence, that can only happen if H0 is trivial on both sides, and the H1F is usually also trivial unless the H1F of M star 1 is also non-trivial. So one is at a central point. That is also a critical point. But if you're not at a critical point, then the fact that alpha M is an isomorphism means basically all the motivic homology spaces are trivial. So there's no regulators involved, only the period isomorphism. Or at the central point, also a height pairing. So it all falls in naturally. So the Deligne periods conjecture is a special case of this. Again, what are the known cases? Certainly the zero-dimensional case. For example, again, by the work of Borel that I mentioned yesterday. Remember, he proved some class number formula up to some unknown rational factor, which amounts to this statement, what I call conjecture rat here. And for curves, yeah, what am I saying here? Shimura curve over totally real F. Why is that known? I guess because of the Gross-Zagier formula, or extended by Zhang to Shimura curves. That basically means that you're at a central point where both the H1FM and the H1FM star are non-trivial, and they're of rank 1, so they coincide with that determinant, and you write down a basis of this determinant by the Heegner point, which gives you the L value. And then there's also a period term taking care of Betti plus and the tangent space. Yeah. So that would be for vanishing order 1, you have a Heegner point. For vanishing order 0, you have just a period. And that's classical. I think that's also known for general Shimura curve, but I'm not 100% sure. Certainly for modular curves, it's known. Okay, so you get evidence for this picture, again, coming from automorphic theory, as always. Yeah, so it can happen that this fundamental line is just Q. Well, it's always Q, you can say it's a one-dimensional Q vector space, but that doesn't mean it's Q. You can only identify a one-dimensional vector space with Q if you have a distinguished basis corresponding to 1. So what I mean here, it's canonically Q. And the way that can happen is if all these spaces of which you take the determinants here, they're actually 0. Yeah, so then the determinant formalism tells you the determinant of 0 is canonically the coefficient ring, which is Q in that case. So you just get Q as your fundamental line if all these spaces are trivial. And that sometimes happens. If you take a totally real field where J less than 0 is odd, and again you take the zeta function case, then there's nothing in the fundamental line. And what that means for the zeta function is that it's actually a rational number. So that happens very rarely, but it does happen. like for the Riemann zeta function at 1 minus n, it's minus bn over n. So it simply says that the zeta value is actually in the coefficient algebra Q. It's not just a real number, it's actually a rational number. And that generalizes to totally real fields by the Klingen-Siegel theorem. And so this is also where p-adic interpolation happens. So if you know the basic examples of p-adic L functions, they start with this formula that I was writing down here with this zeta 1 minus n. And you establish certain p-adic continuity properties of these formulas. So you can say that p-adic interpolation in general happens in the fundamental line. So once you describe somehow in some concrete terms, like by this formula, the L value, and then you can p-adically interpolate it, but the interpolation happens in this fundamental line in general, if the value is not itself rational. Okay. Now we want to describe this a little bit more. I mean, so far we described the value only up to an undeterminate rational factor. Now, how do you describe it up to sign? And so this is done prime by prime. So prime L is the coefficient prime L. And then you define certain complexes from Galois cohomology, which is this F cohomology already, which has appeared in some other talks. So first it's defined locally. And again, the subscript F should mean it's some kind of cohomology coming from an integral model. And if L is different from P, that's exactly what it is. So this would be the push forward of your sheaf ML from the generic point to ZP. And then you take its Galois cohomology. That's exactly what this is. And it looks like an Euler factor. It's this two-term complex. I mean, it's just the cohomology over the ring of integers or the residue field, which is the same if L is different from P. But if L is equal to P, it's a whole different universe. One has to again use constructions from p-adic Hodge theory to define this F cohomology. And again, this was a key insight of Bloch and Kato when they first did this, that p-adic Hodge theory plays this crucial role. I don't want to say more about this construction. So D de Rham is a construction that associates a filtered vector space to this Galois representation ML. But let's everything leave it as a black box because it would be too much of a distraction to say more. And this F cohomology has a map to the usual Galois cohomology R gamma QP ML. And you define the mod F cohomology or the singular cohomology as it was called sometimes yesterday as the mapping cone. And then one has various other distinguished triangles now involving global Galois cohomology. So R gamma Z1 over S ML is just the usual Étale cohomology of this sheaf given by the analytic realization by this Galois module ML. And again, you can view it as Étale cohomology over Z1 over S or as Galois cohomology of the Galois group unramified outside S. But you have to modify it into compact support cohomology, which is just a mapping fiber of the map to all the local groups. And similarly, the F cohomology, the global F cohomology, R gamma F QML, is defined as the mapping fiber to the map of the local singular or mod F cohomology complexes. And so if you put these two together, you get this triangle 1, which I will have to refer to again, relating compact support with the F cohomology. Again, roughly you should think of this as coming from the ring of integers, or it's some kind of cohomology of Z of the sheaf ML. And going to the local F cohomologies. Okay, so that's just some manipulations in Galois cohomology. And then to relate this to the spaces in the fundamental line, one has to, again, invoke some deep conjectures. So first of all, the H0FM, which was some cyclic group, by definition, some Chow group, if you tensor it with QL, you just get the Galois invariance, the H0 QML. So that's a kind of Tate conjecture. And Bloch-Kato made an analogous conjecture for the H1. Again, if you tensor it with QL, again, this is some K group. And on the right-hand side, you have some easy Galois cohomology group, H1F QML. Again, this is the group appeared yesterday in Yifeng's talk. And so once you assume that, you have a similar story. So you tensor now not with R, but you tensor with QL, all your spaces in the fundamental line. And you again get an isomorphism. First of all, I should say this. So this conjecture mod L only describes the Galois HIF in degrees 0 and 1, but by this duality, it also describes it in degrees 2 and 3, but involving the dual motive. And so then you've described it in all degrees. And it's exactly the motivic cohomology spaces appearing in the fundamental line that also appear in this Galois cohomology HIF complex. Okay, assuming that, now we can construct an isomorphism of the fundamental line tensored with QL with this compact support cohomology, right? And the key is again this triangle 1. So once you pass to determinants, the determinant of R gamma C becomes a product of determinants of the other terms in this triangle 1. And the other terms, by definition, involve all the spaces in the fundamental line. So the global R gamma F involves the motivic cohomology. The local R gamma F at L equal P involves the tangent space, and the local R gamma F at P equal infinity involves the Betti space. And the other ones are trivialized by this Euler factor. The Euler factor is canonically trivialized because you have two terms in consecutive degrees which are identical. So it's trivialized by the identity map if you take its determinant. So you see all terms in the fundamental line occurring again in this triangle 1. And so that's why you get this isomorphism theta L to R gamma C. And so the integral conjecture then for all primes L is that the L value, which we know lives in psi of M, so you can map it to psi of M tensor QL, so you map it into R gamma C, and there it should span the integral R gamma C. Once you pick some lattice in the Galois representation, some TL in ML. It doesn't depend on the lattice because the R gamma C of a finite module has trivial multiplicative Euler characteristic, and the determinant, as we saw yesterday, recovers the multiplicative Euler characteristic. So that's what this formalism does for finite modules. And if you make this conjecture for all primes L, of course, you pin down this L value actually up to a sign, because you pin down the analytic valuation of your indeterminate rational factor for all primes L. So it's a very elegant formalism, and I think it points to, well, maybe to some progress improving things. And I hope to give some more evidence for that in the last two talks. But it looks a little bit cryptic from the point of view of concrete formulae, I have to admit. So when is this known? As I was saying yesterday, it's known for the Dedekind zeta function because it does reduce the analytic class number formula at both 0 and 1 by the functional equation. But this formalism is completely insensitive to whether the zeta function converges or not. It's uniform. It works for negative integers as well. Yeah, so if you take Dedekind zeta function away from 0 and 1, you don't know it in general, only for cyclotomic fields, or then by standard arguments also for subfields. So in other words, for abelian extensions of Q. And similarly for abelian extensions of imaginary quadratic fields, you can also probably prove it completely, even though it hasn't been written down, I think, but I should be able to prove it completely. And then again, for elliptic curves, well, that reduces to Birch-Swinnerton and Dyer, even though it looks very different, but it does reduce to Birch-Swinnerton and Dyer. And Yeah, and here I'm probably not quite up to date. So BSD in the rank 0 case, as I was writing here, is known for semi-elliptic curves by Rubin's work, basically. Was recently completed by Ashe and myself for all primes, so there's no exceptional primes left. It's completely known. And for non-CM curves, I think it's also completely known for many cases, maybe semi-stable curves in the rank 0 case. I don't know exactly. Other people know more about this. But that gives evidence for this picture. Okay, so I haven't told you all about this formalism. It goes actually much further. So far, I've only talked about motives with coefficients in Q. But very often, your motive is acted upon by some natural algebra of symmetries. So you have some algebra A, a finite dimensional semi-simple Q algebra, which acts everywhere because it acts on the motive. For example, an abelian variety, and you take the H1 of an abelian variety, then the endomorphism ring tensored with Q will act on this H1. It won't act on the higher HIs, but only on the H1, because we want a linear action, not only a multiplicative action. Another example, if you have a variety on which a finite group acts, and of course there's tons of examples, but one example would be if you just have a base change, so X is a base change of some X prime to a Galois extension, then the group ring QG will act on everything, on all the realizations and on all the motivic cohomology groups, just by functoriality. And so to continue, I would just assume that A is commutative, and so a semi-simple algebra is just a product of number fields. So you have some product of number fields acting everywhere. And you can now imagine that what I said so far works with arbitrary coefficients. So I was taking determinants over QL, for example, here. But I could just take determinants over A tensor QL, where A is acting on everything, and so on. So I can make an A equivariant L function using an A equivariant Euler factor. And this A equivariant L function will take values in A tensor C. So if you tensor such an algebra with C, you could just get a product of copies of C indexed by the embeddings tau. So it's a tuple of L functions, a tuple of complex L functions. But you should view it as a single object. And the vanishing order would be an integer valued function on each of these components of A of C. So potentially you get a different vanishing order for each factor. So that's the vanishing order. And the leading coefficient similarly would not be a real number, but a number in A tensor R cross. So it would lie in the infinite places of these number fields EI. I mean, that's fairly straightforward because just take determinants over these coefficient rings A. And you can make also the sequences mod infinity, mod L A equivariant. They should be if everything makes sense. So you get an isomorphism A theta infinity between AR and this A equivariant fundamental line. And similarly for the L-adic story. And then you have equivariant refinements of all the conjectures I mentioned so far. And they're really refinements. They imply the non-equivariant conjectures by taking some norm. So the vanishing conjecture would say that, again, the vanishing order is given by the dimension function over A, and so on. The integrality conjecture is a bit more interesting because now you have to fix some order in your semi-simple algebra A. And you cannot take an arbitrary order because you want a perfect complex. You still want to take the determinant over the order tensored with ZL of this compact support cohomology. And so this can only make sense if you have a perfect complex. And if your ring is not regular, this is not automatic. But it is true if you find a projective lattice in your Galois representation. So projective over the order A tensor ZL. And the projectivity of TL over A will translate into perfectness over this whole complex. And so, for example, this applies to the group, to the Galois extension case I was mentioning. So now you throw in the Galois action on a number field, and you get the A equivariant L function would be a tuple of Rt in L functions. And you get a conjecture over the group ring CG, which somehow mixes the leading coefficients of all the Rt in L functions associated to this Galois extension. And so this is finer than the class number formula. It's not even known in the class number formula case where J is 0 and 1. There it reduces to what people call the Stark conjectures. But again, it's known for abelian extensions of Q. So again, there's evidence that this is actually correct, this straightforward generalization to equivariant L functions. Oh gosh, I'm way behind time. So maybe I'll just say a few words about the non-commutative situation. So I was explaining that A should be commutative here, so the determinants make sense. You cannot take determinants over a non-commutative ring, but there is a substitute of it, which involves quite a bit of K-theory, an idea going back to Deligne called the category of virtual objects. It's basically the one truncation of the K-theory space. So the K-theory space had homotopy groups in pi 0, pi 1, and so on. This only has a pi 0 and pi 1. So you can view it with the geometric realization of a groupoid. And then you have a universal determinant functor, which you can work with, replacing this determinant functor with values in graded invertible modules that I was explaining last time, right? So in the commutative case, if you have a semi-local commutative ring, then this universal determinant functor coincides with the usual graded determinant functor with values in graded line bundles that I was explaining yesterday. But this is only for commutative semi-local rings. So it's pretty special, the situation. But all these rings that we take determinants over, these A and its localizations, and also the order fractional A tensor ZL, they're actually semi-local rings in the commutative case. So the determinant functor coincides with the usual graded determinant functor. And so that suggests in the non-commutative case, you just use the universal determinant functor to make these conjectures. And again, there is some evidence, although only very, very little, coming from variants of the Stark conjecture, that this holds true, actually. Again, over the group ring for a non-commutative Galois group, you make these analogous conjectures, and they should work with non-commutative Galois groups. Okay. Yeah, so that's kind of the end of the general formalism. Now let me come for the remaining few minutes to proven cases. And the way these cases are usually proven is, again, finite dimensionality is a huge unknown conjecture. So, so one usually reduces to situations where the expected rank of the motivic cohomology is just 1. And one only has a motivic cohomology group H1F in this sequence mod infinity, and the Deligne cohomology, which is the co-kernel of alpha M. So only 2 non-zero terms, and the rank of Deligne cohomology is 1. So that means the expected rank of the motivic cohomology is also 1. And you can just write down by some construction an element in the motivic cohomology. For example, a Heegner point, or a Beilinson-Bloch element for higher twists of curves. And so you forget about finite dimensionality. You just replace motivic cohomology by this one-dimensional space generated by your concrete element that you can construct. And this is what's called the weak Tamagawa number conjecture. You just construct concrete elements and then work with them and show that the regulator is related to the L function. And again, this is known for modular forms, I think quite generally. Going back to the original work of Bloch-Beilinson. And then the integral conjecture in that case would follow from an Iwasawa main conjecture if it's completely proven, but I'm not sure for which primes it's proven, but certainly there are some cases. So one gets evidence for these conjectures from for modular forms again, not only at the central point, but at all twists J. Yeah, so I wanted to say a little bit more about Dirichlet L functions, how these fit in this formalism, but again, that's a longer story, so I don't know how much I can say. So again, from the point of view of geometry, Dirichlet L functions are associated to cyclotomic fields. Again, we would like to make everything equivariant with respect to the Galois group of the cyclotomic field, which is just a Z mod MZ cross. And so the algebra A I was talking about, the group algebra, splits into a product of cyclotomic fields, Q of chi, corresponding to the rational characters of this finite abelian group. The equivariant L function is just a tuple of Dirichlet L functions, as I was mentioning yesterday, L eta of S. So the Dedekind zeta function would be the product of these, or the norm of this equivariant L function. The vanishing order conjecture is known. So the vanishing order at S equals 0 of a Dirichlet L function is 0. So the function is non-vanishing if you have a trivial character or an odd character. And for a non-trivial even character, the vanishing order is 1. And that's also exactly the rank of the units, the corresponding eta eigenspace of the units. So that's what the vanishing conjecture amounts to in this case. And that's all classical computations. And the leading coefficient, well, in all cases where one can prove anything, you have to have some kind of formula for the leading coefficient. You cannot use the definition as an Euler product or something directly. And for Dirichlet L functions, there's classical integral representations and so on. And you can, for example, express the value at 0 as this Stickelberger element, as it's sometimes called. So it's a certain group ring element of the Galois group of the cyclotomic field where you apply the character eta. And this parenthesis is just the first Bernoulli polynomial. And similarly, the vanishing order in the case where the function does vanish from non-trivial even characters is basically the log of a cyclotomic unit. And so that means now if you write down the fundamental line for this motive, it has a motivic cohomology of the dual, which is the units, again, tensor with a corresponding eigenspace Q chi. And it has a Betti space, which is this group X V infinity, which is basically the direct sum of over the places. And then you take the sum 0 subspace. So you take the free abelian group on the infinite places, and then in there you take the sum 0 subspace. That's what your Betti space will amount to for non-trivial even characters. And then for the other characters, we're in the situation I was mentioning before, where all the spaces are 0 in the fundamental line, and the determinant just becomes the coefficient ring, which is Q of chi in that case. So the L value is a number in the coefficient ring Q of chi. That's what it is by this formula. So you have this very different behavior for even and odd characters, for Dirichlet L functions at S equals 0. But you put them all together because remember we're viewing this whole motive together with its group action. So you have to take all characters together as a package. And so you express the leading coefficient in this fundamental line as a section of this fundamental line. So that's what the last line of this slide does. So you have a certain cyclotomic unit, and then sigma m is a canonical embedding, a canonical infinite place that you choose in the even characters. And then for the other characters, you just take the L value. It's already in the coefficient ring. So it's already in the fundamental line. So that proves the rationality conjecture just by inspecting these formulas. And to prove the integrality conjecture, one uses Iwasawa theory. So I'm probably running out of time, so let me summarize this. So this compact support cohomology, where we, for some reason here, I dualize it to get more concrete groups. So I take this delta of f of m is the dual of this compact support cohomology. And then you pass to the whole cyclotomic tower for your given prime L. You take this whole situation over the L cyclotomic tower, and then your group algebra that was acting on a finite level becomes the Iwasawa algebra on an infinite level. Not necessarily regular, because you really take the group ring. And similarly, your whole perfect complex becomes a perfect complex over the Iwasawa algebra by taking the inverse limit. So I call this delta infinity. And now, remember, we express the L value in the fundamental line, and you also take the limit of all these expressions in the fundamental line. So you get a norm-compatible system of cyclotomic units called eta M0. M0 is the prime to L part of M. Living in the H1 of this complex of delta infinity, which is just the inverse limit of the units. You have the inverse limit of these compatible embeddings in the cyclotomic tower, which lives in the H2. That's for the even part. And for the odd part, you have the inverse limit of this Stickelberger element, which is one way to construct a periodic L function, if you recall this. And this is, again, just a number in the coefficient algebra, not quite in lambda, but in mild localization of lambda. So it's something in the coefficients made from the Stickelberger element. And the H2 also involves the class group. So if you compute the cohomology of this complex, you get the inverse limit of the class groups, which is a classical Iwasawa module. But you also have this X infinity, which is not torsion over lambda. It has the same rank as the H1 delta infinity. It comes just from infinite places. It's a very simple module. Okay, so the total quotient ring of lambda also splits into some eigenspaces for the characters. And you have a total LIDL function, which is just some kind of inverse limit of all these sections. If you take all these sections here and pass to the limit, you get a basis of the determinant, which is some kind of LIDL function, but involving all the characters of conductor dividing M0 and L power conductor. So you have this very different behavior for odd and even. In the odd part, you'd get the Stickelberger element. In the even part, you get a system of cyclotomic units, basically. And so the main conjecture would be saying that the integral determinant is also spanned by this LIDL function. So it's kind of completely parallel to the Tamagawa number conjecture, the way I've presented it. So also Iwasawa main conjectures fall into a similar framework that a certain section given by an LIDL function spans the determinant of some integral complex over the Iwasawa algebra. And so the way this is proven, you can check this prime by prime. So if you localize at height 1 primes of the Iwasawa algebra, this statement here essentially amounts to an identity of characteristic ideals. For example, in the even components, the fitting ideal of the inverse limit of the class group should be the units modulo cyclotomic units. So that's one way of phrasing an Iwasawa main conjecture. And in the odd components, the class group should be given by the Stickelberger element. And this was proven by Maser-Weil. So this is how you relate things to classical Iwasawa theory, by passing to this inverse limit. And so there's a slight twist. So if you have a height 1 prime of the Iwasawa algebra, which contains the prime L, so this was what's traditionally related to the mu invariant of the Iwasawa models. If L is odd, then the fact that mu is 0, which is a theorem, proves you the main conjecture as formulated here. But if L is 2, you have a problem because in this case, you really have to work with a perfect complex. You cannot pass to cohomology. The cohomology modules of this complex delta infinity localized at Q, they're not themselves perfect over the Iwasawa algebra. So so this is much harder case, but it can be shown to be true by completely different computations using some classical results of Coleman and Leopold and so on. So eventually what it amounts to, I mean, if you look at the two primary story, there must be some congruence between the odd part and the even part. In other words, between these Stickler elements, theta m0, and the cyclotomic units, eta m0. There must be some kind of mod 2 congruence between these. That's implicit in this main conjecture. And to make it explicit, one can express it by some, after many computations, which I did, it amounts to a fairly elementary statement. So if you take this complex number as it's written here, for some x between 0 and 1, it has a certain sign. It's actually a real number. And its sign is given by this -1 to the floor of x times m. And this is also what happens, what describes the Stickelberger element. So this is a cyclotomic unit where you apply a certain element in the Iwasawa algebra, gamma minus chi cyclo of gamma. And yeah, and this floor is also what occurs in the Stickelberger element. Okay, so this bizarre determinant formalism is confirmed by very concrete computations. So there's some kind of mod 2 congruence between the even and the odd characters in these Dirichlet functions at the prime 2. Okay, and then once you prove the main conjecture, you descend back down to get the Tamagawa number conjecture. And the descent is fairly direct very often because you just have a natural homomorphism from the Iwasawa algebra to a finite group ring, and you tensor the infinite complex over this morphism, and you get back the original R gamma C. And then you're left with computing the image of this Pierre-de-Gell function. And very often it just coincides with the section that we've started out with at the beginning. And but not if there's trivial zeros of the Pierre-de-Gell function. So one needs extra theorems to make a complete proof, but very often it's straightforward, but not always. Especially at n equals 0, because then you get trivial zeros of the Dirichlet functions. Okay, and so again, for n less than 0, the descent is direct. For n equal to 0, it's less direct. You need some complicated theorems. And for n bigger than 0, you cannot descend directly because basically of non-vanishing of Pierre-de-Gell functions, which is not known in general. But one proves compatibility of the conjecture with the functional equation, and so you also get it for n bigger than 0. So for Dirichlet function, the conjecture is known at all integers n by Iwasawa theory. I guess I should be stopping, right? I have a few more cases where the conjecture is proven. Elliptic curves, of course, a whole different story using work of Skinner, Urban, and Kato. The full BSD formula is also known in many concrete cases, some infinite families. Adjoint motives of modular forms are known by work of Diamond, Guo, and myself. Again, with some restrictions on the prime L, using the Taylor-Wilds method. And many motives associated to automorphic forms are known, like in Yifeng Liu's talk yesterday, or at least partially known, partial statements towards this conjecture. Certainly the integrality conjecture is known in only very few cases, especially for all primes L. Dirichlet functions is kind of the main case where it's known for all primes L. And Hecke functions of imaginary quadratic fields. Okay, I think it's time to stop.
Are there any questions, comments?
Just a vague question in general, H1M and H1FM, is there some expectation about the difference between the two?
Oh, yeah. Very good. At the central point, there's certainly a difference, but not at the other points. Well, no, there's a difference. Let me see. No, also at the other points, for example, an elliptic curve at s equal 2, that was the first example discovered by Bloch and Grayson, that there is a difference in the rank between the H1FM and the H1M coming from bad reduction.
Oh, okay.
Yeah. So there is a difference. That's all I can say. I don't have it in my head when they are the same. I think if the twist is big enough, they are the same. But there's a difference in general. And it's awkward to have to refer to a regular model. But yeah.
Any further question? Okay, it seems not. Then let's thank Matthias once again.
Okay, thank you very much.